So this is the last of the possible directions that you would normally see for inverse trig functions. And this one is the least specific of all of them. This one's all possible values, which means you're going to give every single angle that could potentially give you that value. And a lot of people think that that's the same thing as full circle values, but full circle is only between 0 and 2 pi. Remember, the unit circle goes on forever and ever and ever. You can always continuously spin more and more and more. One full circle is 2 pi radians, 2 full circles is 4 pi radians, then 6 pi and 8 pi, 10 pi, all the way up to 46,412 pi. So you can always go more and more circles, but you can also go backwards all those circles. So you can go to 0 radians, and then negative 2 pi radians, and then negative 4 pi radians, all the while going forwards and backwards on those circles. So that's where things start to get tricky, because all of those are coterminal angles. So you're always going one more circle or one less circle. So let's go ahead and remind ourselves real quickly about the periods of our functions. So here's a little chart. The period of the function sine of x and cosecant of x both have a period of 2 pi. That means every 2 pi radians, those values start to repeat themselves again. For cosine and secant, it's again 2 pi, so every 2 pi units it starts to cycle again. But for tangent and cotangent, again, those two have to be different. They're always messing with us. But for those ones, it repeats every pi units. So this is what we're going to end up using for everything, so I would strongly suggest pausing the video and quickly writing yourself this little note if you don't have it already known to you. So let's look back at those problems again. So these are again the same exact problems that we've been looking at, and we start the same way for every single problem. We always start by taking the inverse sine or the arc sine of both sides, because that will give our theta by itself. So now as we look through here, we're going to again ask ourselves, when does sine equal root 2 over 2? Well, that happens right here and right here at pi over 4 and at 3 pi over 4. But here's the issue, is it's not just pi over 4. I could also add 2 pi to it and get 9 pi over 4. And over here, I could get 11 pi, ooh, it's not pi, 11 pi over 4. Then I could add another circle over here, and I could get 17 pi over 4. And I could keep going back and forth, adding and adding and adding, but I could also go back and forth, subtracting and subtracting and subtracting. So if you were actually to write out every single angle, it would take you forever. You'd be there an infinite number of times just to write the positive ones, and then again infinite amount of time to write the negative ones. So we came up with a little bit of a shorthand. We're going to say that theta is equal to, and we're going to start with one of them. Let's start with pi over 4. We're going to say you could always add a full circle to it. Or you could add 2, or 3, or 4, or 5, or 6, or 7, or 8, or whatever. So we designate that with the k. This is the number of circles. So this is any integer number of circles. So we have to write ourselves a little note. And it's not just for us, it's for anybody who's reading our paper. K is equal to all real integers. If we're going to introduce some sort of variable or some sort of unknown, we have to give them an idea of what it is. So k can be any number that is a real integer. Because now, if whoever's grading our paper wanted to know what the 4th iteration of this would be, then it would be pi over 4 plus 2 pi times 4. But remember, they don't just add circles, you can also subtract circles. So we take this value and we add and subtract a full circle, because that is when that's the period of that function. So that works for pi over 4. That'll give me pi over 4. It'll also give me the 9 pi over 4 and the 17 pi over 4 and so on and so forth. Let's do the same thing for the 3 pi over 4. you can always add or subtract a full circle or as many of those as you want. So plus or minus 2 pi k is kind of the idea here. And k is just a letter I use. You can use any letter you want as long as it's not already previously defined. So you could use theta, you could use k, you could use L, M, P, Q. You could use some Greek symbols, it doesn't matter. As long as you say up at the top of your page, k is all real integers, or theta is all, or sorry, not theta, you can't use theta because it's already in the problem here. Whatever you decide to use, make sure you state what it is. So I'm going to go ahead and say this is for the whole video. So you should be able to write down at the top of your page, k equals all real integers. That way, every time I see k, or every time your teacher or whoever sees k, they know it means all real integers. So this is holding true for my whole page. Now that I've written this down, I don't have to worry about writing it down anymore. So let's go ahead and solve this next problem. Again, I take the inverse sine of both sides. And so now my question is, when does sine equal root 3 over 2? Looking at my unit circle, sine is the y value, so root 3 over 2 is up here and here at pi over 3 and at 2 pi over 3. So I'm going to go ahead and write down that theta is equal to pi over 3 plus and minus the period of my function as many times as you want. And then theta could also equal 2 pi over 3 plus or minus the period of my function as many times as you want. So really this is extremely similar to full circle values. The only difference is going to be when we're getting to those tangent and cotangent functions, because that's where our period is different. So again, when does sine equal negative 1/2? Well, sine is our y value, so y value being negative 1/2 happens here and here. So that happens at 11 pi over 6, and it happens at 7 pi over 6. So I'm going to take both of those values, 7 pi over 6, add and subtract my period as many times as I want. 11 pi over 6, add and subtract my period as many times as I want. So now, again, it's just getting to those practice problems. So from here on out, we're just doing practice problems so that you guys can see a few more worked out examples. Here is our first section of practice problems. In just a moment, I'm going to put up the answers. So just like normal, strongly suggest that you pause the video, try them out on your own, and come back to the video when you're done. So here are the answers to this question. Let's go ahead and see why. Just like all other problems, start it off by taking the inverse cosine. So the question is, when does cosine of theta equal root 2 over 2? Cosine is our x value. It happens right here and right here at pi over 4, at pi over 4 and at 7 pi over 4. So I'm going to take both of those values and say pi over 4, add and subtract my period as many times as I want. 7 pi over 4, add and subtract my period as many times as you want. Let's go ahead and switch it up and put arc cosine this time. So when does cosine of theta equal root 3 over 2? Well, cosine is your x value, so x is root 3 over 2 here and here at pi over 6 and at 11 pi over 6. So I'm going to take those values, pi over 6, and I'm going to add and subtract my period as many times as I want. 11 pi over 6, add and subtract my period as many times as I want. We'll go ahead and stick with the arc cosine to get that theta by itself. So now when does cosine of theta equal -1/2? Well, cosine is the x value. That happens up here and down here at 2 pi over 3 and at 4 pi over 3. So I take my theta, here is my first angle, add and subtract my period as many times, 4 pi over 3, add and subtract my period as many times. So these first 6 were all kind of straightforward. Now we're going to look at those 3 slightly different ones, and we'll notice that something different happens on the last 2 that we do. So again, here's 3 practice problems. Strongly suggest take a moment, pause the video, see if you can figure out what that difference is, solve it on your own, and then come back to the video. So here are those answers, and you'll notice the tangent and cotangent look a little different. So we'll get to that in just a moment. But for now, we're going to take the inverse cosecant of 2. So when does cosecant of theta equal 2? Again, that's going to be at the same location that your y value is 1/2, because this is the reciprocal to get that y value. So that happens here and here at pi over 6 and at 5 pi over 6. So at pi over 6, add and subtract your period as many times as you want. 5 pi over 6, add and subtract your period as many times as you want. Here is the different part. Let's go ahead and start the same way we normally would. Inverse tangent of both sides. And again, our goal is to decide when does tangent of theta equal √3 over 3. On the last few videos, we've decided that it happens at pi over 6 and at 7 pi over 6. But let's think for a second. Because if we scroll back, I'm going to change pages real quick. If we scroll back to here, the period of our tangent and cotangent function is pi. Which makes sense. Anytime you're solving these types of problems, your values for tangent are always half of a circle away. Because you're always able to add half a circle, add half a circle, add half a circle over and over to get those new values. Which means all we have to do is put down pi over 6, add or subtract its period as many times as we want. A lot of people think that means that we're neglecting 7 pi over 6, but we're really not. Because if you take pi over 6 and you add pi, so what we're going to do is we're going to say where k equals 1. So it's pi over 6 plus pi. Well, in order to add fractions, you find a common denominator. 7 pi over 6 is already included in this answer choice. So we don't have to do 7 pi over 6 plus or minus pi k. That's just extra information. It's reiterating what we just said. 7 pi over 6 is when k is 1. And that's why we only need one answer for this. And we'll end up with the same thing here for the cotangent. If I do arc cotangent of -√3, then I'm asking myself, when does cotangent of theta equal -√3? Again, previous videos we found out that it happens here at 5 pi over 6 and here at 11 pi over 6, which again is halfway away. So I take one of those answers and I add and subtract the period of the function as many times as I want. Again, if you don't believe me that 11 pi over 6 is included in that already, I'm going to take 5 pi over 6, and I'm going to say when k equals 1, then I am adding pi. So 5 pi over 6 plus 6 pi over 6 will give me 11 pi over 6. 11 pi over 6 is included inside of this answer already. And that's the strange thing for these all possible values, it actually makes tangent and cotangent a lot easier. So yes, they are different, but it actually makes the answering easier.